Welcome back. In this section, we're going to talk about graphs of the sine and cosine functions and also transformed sine and cosine functions. Here, when we're thinking about our basic shapes of these functions, we're going to think in terms of that unit circle definition. And that means that for the sine function, we're going to be thinking of it as the y value as we make our way around the unit circle. So at 0 radians, our y value is 0. At pi over 2 radians, the y value is 1. Then 0. Then negative 1. And then back to 0 again. And there's actually quite a few properties that we already know about our sine function, in part because of what we've seen before, and also just thinking again in terms of that unit circle definition. So the first part, the domain, why the domain is all real numbers. Remember that sine is the y value on our unit circle. And it doesn't matter which angle you're thinking of, for the point that's on the unit circle, there is always a y value, which means that we can always find the value for sine. So yes, the domain is all real numbers because that means any angle we'd like to look at, we can put that angle into sine and get some sort of an output. In this case, the output being the y value on that unit circle. If you're thinking about the next part, the range, why the range is from -1 to 1, again, sine is the y value on this circle, and the largest y value is +1, and the smallest y value is -1. So sine never has a y value, sine never has a value larger than +1, because the unit circle doesn't have any y values larger than +1. And sine is never less than -1 because the y values on the unit circle are never less than -1. We also know stuff about the x and y intercepts. The y-intercept, we found that on the previous page. We know that when the x value is 0, the y value is 0, so that's where that came from. We also found a bunch of x-intercepts when x is 0 or pi or 2 pi. But because we know that sine is periodic, because sine repeats itself every 2 pi radians, then if these 3 points are x-intercepts, then pi plus 2 pi would be an x-intercept, 2 pi plus 2 pi would be an x-intercept, 3 pi plus 2 pi would be an x-intercept, and same thing with subtracting full circles. Pi minus 2 pi or negative pi, that would be an x-intercept. 0 minus 2 pi, negative 2 pi, that would be an x-intercept, and so on. So all of these points would all be x-intercepts, or in other words, the x-intercepts happen whenever x is some whole number multiple of pi or some negative whole number multiple of pi. So plus or minus pi, 2 pi, 3 pi, 4 pi, and so on, as well as when x is 0. The other two little facts, we knew those from earlier, that sine was an odd function and sine had a period of 2 pi. So our sine function then has this look. And notice that if we're thinking just in terms of what I had from the first slide, the y values of 0, then 1, then 0, then -1, then 0, that defines one full cycle, one period of my sine function, and notice that it repeats itself, and it will repeat itself again and again and again and onwards forever. So here, when we're graphing our sine or our cosine function, we obviously can't graph the entire function because that would be graphing for all x values. So we're going to limit ourselves to graphing usually one full cycle or 2 full cycles of our sine function. And same thing with any other trig function we're graphing. One thing I want to draw everyone's attention to before we go further, you'll notice here that when I'm looking at sine as a function, when I'm thinking about y equals sine of x and thinking about this, I'm always thinking about x the angle being measured in terms of radians. So notice that on the x-axis, I have pi over 2's and pi's and 3 pi over 2's rather than 90's and 180's and all the rest. So this is true whenever we're graphing trig functions, and in fact, in general, whenever we're dealing with trig functions in calculus, you'll be dealing with them where the input, where the domain is real numbers, or in other words, radians. So here we will not be using degrees on our x-axis. It will always be radian measurements for our angles. Okay, so we could do the same sort of thing with cosine that we did with sine, just keeping in mind that cosine of x is defined as the x-coordinate as we travel around our unit circle. So the x-coordinate is 1, then 0, then -1, then 0, and then back to 1 again. And the properties we have, the domain is, again, all real numbers, because no matter which angle you're looking at, there will be an x-coordinate on the unit circle. So in other words, any angle can go into the cosine function just fine and give us an output. The range is from -1 to 1, because -1 is the smallest x value on the unit circle and 1 is the largest x value on the unit circle. And since cosine is the x value, cosine can't be any larger than 1 or smaller than -1. We also know that we've got our y-intercept at 0, 1, and that's just coming from our little table of values that we have up top. And we might have noticed that we're crossing the x-axis at multiples of pi over 2, odd multiples of pi over 2. At pi over 2 and 3 pi over 2, but it will also be at 5 pi over 2, 7 pi over 2, and so on. Also, the negative versions of those angles as well. So all of our x-intercepts, plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on. And then finally, the symmetry, we knew from before that cosine was an even function, and that it has a period of 2 pi, just like sine. So our graph for our cosine function looks a little like this. Putting in, again, our values that we had of 1, then 0, then -1, then 0, then 1. That gave us one full cycle of our cosine function. And we can see that we have, again, another cycle just to the left of it. And you can see the nice even symmetry of our cosine function, symmetric around the y-axis. And there we go. One thing you might have also noticed about this is that our cosine function looks similar to our sine function. In fact, if you're thinking about taking your sine function, and if I were to just shift it to the left by pi over 2, that would give me exactly the same graph as my cosine function. So although they are different functions, the graphs of them are really, you can think of them as related to each other. That the cosine function has the same kind of shape as the sine function, it's just shifted over a little bit from where the sine function is. All right, so we're going to start talking about transformations of our trig functions and transformations of sine and cosine and all the rest. And when we do, we have some special terminology here. So if you're looking at, as we've defined these functions, y equals a times sine of bx or a times cos of bx, we know that a, that would be a vertical stretch. That would stretch our graph, and if a happened to be negative, that would stretch and also reflect our graph vertically. You also know that the number b in front of the x, that has something to do with a horizontal stretch. That's going to compress or stretch our graph horizontally. So a couple of things to note here. We can say that this value of a, when we take the absolute value of it, we can call that the amplitude of our sine and our cosine function. Remember that our sine and cosine function, normally their maximum value is 1 and their minimum value is -1. So you would normally say for y equals sine of x, you would say that the amplitude would be positive 1. And if you're thinking, what does that represent? The amplitude represents the distance from the middle of that trig graph to the maximum value that it has, which is 1 unit. If you have a number in front, that's going to stretch your graph vertically, which of course is going to increase your amplitude. So something like y is equal to 2 sine of x would be something that, instead of reaching maximum values of 2 and instead of reaching maximum and minimum values of 1 and negative 1, that would now have maximum and minimum values of 2 and negative 2. And so for that function, you would say that the amplitude is 2. For the value b, we know that that is some sort of horizontal compression or horizontal stretch. If b is a positive number, then it's a horizontal compression or horizontal stretch. If it's a negative number, then it's a horizontal flip as well as a stretch. And if you're thinking about what a horizontal compression would do to things, if you're thinking about, for example, sine having normally a period of 2 pi, that's how soon it makes one full cycle. If you were to stretch or compress this graph horizontally, if you were to stretch it out, then you'd be increasing the period. You'd be making it take longer before the function repeats itself. Or if you compressed it in horizontally, you'd be shrinking that period and making it repeat itself more frequently. And so one thing that we know, of course, is that if you're thinking in terms of transformations, when you're doing a horizontal transformation, you're dividing every x coordinate by that value. So not a big surprise then that when we're talking about our period, the period is 2 pi, the original period, divided by absolute value of b. The reason that we're using absolute values for both of these, amplitude is a measurement of size or distance. So amplitude, we really do want it to always be a positive number. So even if you had something like y is equal to negative 2 sine x, you would still say that the amplitude is positive 2. Same thing with period. Period is a length or a distance. It's how long does it take horizontally before the function repeats itself. So not a surprise there. We're also using absolute values. Okay, so let's find the period and amplitude for these two functions. Firstly, the amplitude, we find that by taking the absolute value of that coefficient negative 3. So in other words, the amplitude here is positive 3. The sine of x over 7, of course, you could think of that as being sine of 1/7 times x. So here the value of b that we're thinking about is 1/7. So if you're thinking about the period, that would be 2 pi divided by absolute of 1/7, which is the same thing as 2 pi times 7 over 1, or in other words, 14 pi. So this is a sine function that's stretched out by a factor of 7. It's 7 times longer than it originally was. Normally our sine function repeats itself every 2 pi. This sine function repeats itself every 14 pi. It takes much longer for it to repeat itself. Let's do another one here. We've got y is equal to half cosine of negative 4x. And you can say that the amplitude then should be absolute value of a half, which is a half. And that our period should be 2 pi divided by absolute of negative 4. Or 2 pi over 4, or pi over 2. So this cosine function repeats itself every pi over 2, every 90 degrees. So it's actually 4 times narrower. It's compressed in by a factor of 4. And of course, we should be able to go backwards here. Here, I'm going to be thinking about describing this function with an equation, and I'm going to think about describing it as a transformed cosine function. And the reason I'm thinking about that is because if you're thinking the basic shape for our cosine function, it has the same kind of shape as the graph that we have here on the left, starting at the top and then going down and then back up again. So the one thing to note here, of course, is instead of going between +1 and -1, we're instead going between +3 and -3. So it looks like for this function that the amplitude is 3. Also, if you're thinking in terms of the period for this function is pi. So basically what I need to do now is come up with a cosine function that has an amplitude of 3 and has a period of pi. And if I'm thinking about the amplitude of 3, that one's the easy one to take care of. I know that my function will be y is equal to 3 times cosine of something times x. I just need to figure out what that value of, in this case, b is. I know that for my period, it should be 2 pi divided by absolute value of b. And I know that my period here is supposed to be pi. So I can use that to solve for what my absolute value of b needs to be. And I can find that absolute value of b needs to be 2. So here I do have two options. I could say that b is +2, or I could say that b is -2. And the reason why it doesn't really make a difference whether I say b is +2 or -2 is because we're talking about a function that's symmetric around the y-axis. Remember that if you were to take b as being negative, if I were to say that y was 3 cosine of -2x, the negative would be referring to reflecting things around the y-axis. But since we're symmetric around the y-axis, then you know that cosine of -2x and cosine of +2x should look exactly the same. So we do have two options here as far as the value for b. We could take +2 or -2. For the value of a, I have to take +3 rather than -3. -3 would have not just stretched things, but would have also reflected things. This would be a graph where we have a -3 times cosine of 2x. So for my function here, the one that has the correct amplitude and correct period, I'll say that it is 3 cosine of 2x, or you could say 3 cosine of -2x. And these are not the only two options. If you're thinking back to what I said at the beginning, how a sine graph looks like a cosine graph that's been shifted to the left or to the right, we could, so if we were feeling particularly clever, we could also come up with a way of describing this as a sine graph that has not just been stretched vertically and compressed horizontally, but has been shifted to the left or to the right. But I'm not going to go for a more difficult kind of an answer. I want to go with the most straightforward answer to this one. And so for this, either 3 cos of 2x or 3 cos of -2x.